Hello, this is Dr. Maxwell, and this is our first online lecture. We are covering section 3.1 from your book. You can find this on Canvas. Check your email for more details. This is an example I like to use to help us understand what a one-to-one correspondence is. So, here we go. Imagine that there is this theater complex. I'm calling it the TriStar Theater Complex. And there are three movie theaters. I'm just calling them A, B, and C. And suppose maybe you're at the movie theater and you're going in to look for a friend and you don't know which theater the friend is in. So you have to look in each theater. But you notice something else when you do this. So first you look in theater A, and you notice that some of the seats are occupied, but there are a lot of empty seats, and no one is standing. Okay, you sort of take note of that. Then you go to theater B, and there you see every seat is occupied. This movie must be really popular. None of the seats are empty, and there are also people standing up in the back, standing room only. That's what we used to say. And then in theater C, the situation is different once again. Here, every seat is occupied, no seats are empty, no one is standing. And we're also operating under the assumption that it's one person per seat. There's not like somebody with a child in their lap. No two people are sharing seats. So, one thing we don't know is how many seats are in the theater, because I'm not going to take the time to count all those, and neither would you. But we do know something about the number of seats compared to the number of people. So we're going to introduce some useful notation. I'm letting S represent the set of seats, and I'm going to let P represent the people. Now we have some really useful notation that we have to learn. If I write S with these two bars around it, it sort of looks like an absolute value sign. This denotes the number of seats. If I do that with P, well, that would denote the number of people. Now, we don't know the exact number of seats or the exact number of people in any of these theaters, but we do know the relationship between the number of seats and the number of people. So what can we say about the relative sizes of the two sets in each theater? Well, let's look at theater A again. Some seats are occupied, but there are a lot of empty seats and no one is standing. So I'm pretty sure that there are more seats than people. Let's think about that. There's seats that are empty, right? And no one is standing. A few seats are occupied. So there are more seats than people. I hope that makes sense. Now let's look at Theater B. Every seat is occupied, no seat is empty, and in addition, there's some people standing up in the back. So there isn't a seat for everyone. There are more people than seats. So this is just the number of seats is less than the number of people. That's what this says. The number of seats is less than the number of people. In theater A, we could say the number of seats is greater than the number of people. Okay, now let's look at theater C. Here, every seat is occupied. No seats are empty. No one is standing. So there is a seat for every person, and every person has a seat. So these numbers are equal. The number of seats equals the number of people. Okay. So what we're really interested in is this situation that is occurring in theater C. Every seat is occupied, no seats are empty. The number of seats equals the number of people. And we have to learn some vocabulary here. We are going to say that the sets S and P are equally numerous. The set of people has the same number of objects in it as the set of seats. And how do I know? Because every seat corresponds to exactly one person, and every person corresponds to exactly one seat. And this is a one-to-one correspondence between the two sets, S and P. They can be paired up in theater C. So we really need to understand this concept of a one-to-one correspondence. So when we count the number of objects in any kind of collection, like the number of DVDs in the Harry Potter series, what we're actually doing is forming a one-to-one correspondence between those objects and a subset of the natural numbers. And we just do this naturally. We count things. How many students are in the class? I just count them. So let's look at example 2 and see what I'm talking about. I'm letting HP represent the set of Harry Potter novels. A set is just a collection. So then I'm asking, what is this? What does this mean? Well, this means how many books are in there. How many objects are in the set HP? Well, it turns out there's 7. And so that's why I can write this. The number of objects in the set of Harry Potter novels is 7. And I've listed them here. And if I want to count them, I would just go 1, 2, 3, 4, 5, 6, 7. What we're actually doing is pairing up with a subset of the natural numbers. So when we count the books, we're forming a one-to-one correspondence. Between the novels and the numbers 1 through 7. So every book corresponds to a number, and every number corresponds to a book. So that is the very fundamental aspect of a one-to-one correspondence. Between two sets, you can pair them up so that everybody is matched with exactly one object from the other set. And this is why it's useful. Sometimes we know we can form a one-to-one correspondence between two sets, even though we don't know exactly how many objects are in each set. And that's exactly what we did in Theater C. We didn't know how many people there were. We didn't know how many seats there were. But we know that those two numbers are the same. The two sets are the same size. So when you can form a one-to-one correspondence, it means every object in one set corresponds to exactly one object in the other set, and vice versa. Now here is another important vocabulary word. Now remember, you can pause this anytime you need to take a break, to write something down, write down a question that you might have, and then keep going. Okay, cardinality. When we know that two sets are equally numerous, they have the same number of objects, we say the two sets have the same cardinality. So this, in Theater C, is the cardinality of the set of seats in Theater C. And we knew in Theater C that this number was equal to this number. These are both numbers, and they're equal. We just don't know what number it is. So these are the basic ideas in section 3.1. So a little summary here. We are going to talk more about sets, but you can just think of a set as a well-defined collection of objects. Basically, a set is defined by its objects, by its elements, what is in it. So we need to know what belongs to a set and what does not. We'll also talk about subsets. And for now, we can think of a subset as sort of a sub-collection. A smaller collection of the things in a set. Cardinality is an important word I will use a lot. So what is it? The cardinality of a set tells us how many objects are in the set. Now, when a set is not infinite, like if it doesn't go on forever, then the cardinality is simply the number of objects in the set. And we represent the cardinality of the set A. You write the set and you use these two bars that look like absolute value bars. We also need to understand what a one-to-one correspondence is. This is a special kind of pairing between two sets. It's a pairing where every object in the first set corresponds to exactly one object in the second set and vice versa. And when we can form a one-to-one correspondence between two sets, we know they have the same cardinality. So that is an important idea. It's right here. If we can form a one-to-one correspondence between the two sets, then we know the two sets have the same cardinality, even if we cannot count the objects. Okay, let's do a little practice. These are some practice problems getting the idea of a set. And we have special ways of writing a set. If we're going to list the elements, we use these curly braces, which are kind of hard to draw, and we separate the elements, see if I can do that better, with commas, and sometimes we'll use an ellipsis. So let's just make an example. A says list out the elements, or write out the set of natural numbers less than or equal to 10. So I'm going to have curly braces. So that's 1, 2, 3. Maybe I'm getting lazy. And I just use an ellipsis to indicate we continue up to 10. Now I'm going to call this set A. We usually give sets a capital letter name. It's just a convention. And then I'm going to ask you, what is this? Well, remember what this means. This is asking you how many things are in the set A. What is the cardinality of the set A? Well, it's 10 because there are 10 things in there. Okay, let's look at B. The set of even natural numbers. Well, I'm going to call this set E. And that's my curly brace. The first even natural number is 2, then there's 4, then there's 6, and we cannot write them all down. So I'm trying to draw an ellipsis here, and sometimes it doesn't show up well on the iPad. So let me try this again. It's supposed to be a dot, and a dot, and a dot. Sorry, this is a little fiddly sometimes. You have to bear with me. Now, what does this set represent? This is all the even natural numbers. Okay. Well, what if I ask you for the cardinality of this set? What is the cardinality of E? Well, we don't really know yet. It's infinite. We can say that, but we can't count them. And this is the main idea in Chapter 3. We're going to learn ways to describe infinite sets. Our last example here is the set of prime numbers less than 20. So I'm just going to call this set capital letter B. And then we have to think, what do we remember about prime numbers? Well, the first one is 2. And then the rest are going to be odd. 3, 5, 7. Can we put 9 in there? No. 9 is not prime because 9 equals 3 times 3. So if we jump over 9, 11 works, 13 works, 15 does not, 17, and 19. All right. I hope I didn't leave anybody out. What is the cardinality of B? Well, I'm just going to count them. 1, 2, 3, 4, 5, 6, 7, 8. The cardinality of B is 8 because there are 8 elements in the set B, 8 numbers. Now we'll do a little practice forming one-to-one correspondences. So it says here, determine whether there is a one-to-one correspondence possible between the two sets. If there is, create it. Okay, so let's do this. Let's call A this first set and call B this second set. And the first thing we might want to ask ourselves is what's the cardinality of A and what is the cardinality of B? Well, how many objects are in the set A? 1, 2, 3, 4. How many objects are in the set B? 4. Well, these are equally numerous. That means they have the same number of objects. So there is a one-to-one correspondence possible. So let's just create it. The way we start is by listing the elements. So I've listed the elements in A. Now I'll list the elements in B. The elements in B are these words. Don't let that confuse you. The set B contains 4 words. Now, the next thing we do is pair them. So step 1 is list. Step 2 is pair, if possible. So I can pair A with red, I can pair B with blue, C with green, and D with purple. Of course, there are other ways to pair them up, but this is perfectly good. So there is a one-to-one correspondence between these two sets. And here it is. Okay. Example number 2 says we want to look at the set of prime numbers less than 20 and the set of the first 8 natural numbers. So what I'm going to do is a list and then try to pair. So the prime numbers less than 20, I'll call that the set A. And I think we might need a little more room, so let me write a little smaller. We have 2, 3, 5, 7, not 9, 11, 13, 17, and 19. And you might remember, we just did this back here. I gave it a different name, but it's the same set. And there are 8 things in there. So maybe you have already figured out that this is going to work out. So I'm going to call this set B. What does B look like? Well, 1, 2, 3, 4, 5, 6, 7, 8. And can I pair them? Well, let's see. You just try. We know the cardinality of A equals the cardinality of B. what is that number? Well, it's 8. When two sets have the same cardinality, they are equally numerous. And there is a one-to-one correspondence possible. Last example. See here. Whoops. So look at our picture and see what it says. Is there a one-to-one correspondence between the set of pigeons, let's call that P, and the set of pigeonholes, let's call that PH? Well, how many pigeons are there? I see 1, 2, 3, 4, 5. How many pigeonholes are there? 4. Now, when you know two sets have different numbers of objects in there, they're not equally numerous. There is no one-to-one correspondence possible. It's a long word. And suppose you tried. Well, maybe this pigeon goes into this hole. He goes in here. She goes in there. This pigeon goes in there. This guy obviously has to share with somebody. Maybe he goes in here. But we cannot pair the two sets one to one. So the answer here is no. Okay, what you should do is read section 3.1 of the textbook, try the homework, ask questions. Very important though, please use Canvas email or the Canvas discussion page. If you use a personal email account, I may not get back to you. And if you don't email me through Canvas, even if you're using Forum, it's going to be harder for me to keep track of things because I'm going to have a lot of students sending me a lot of emails. So please use Canvas email or the Canvas discussion page, and that way we have a record of our correspondence. So I hope you're all doing well. Keep in touch with me. Let me know what your questions are, and I will see you soon. Not literally, but in our next lecture, which will cover section 3.2.